Today we're going to talk about geometric power series as functions. Before we can start, what is a power series?
Coefficient times x to a power.
Coefficient times x to a power. What is a geometric series?
R times A over 1 minus.
So it's a times r to the n.
Yeah.
Almost. A is your leading term times some ratio to the n power. So your first term is a and you multiply by r each time. So today we're sort of going to link these two, power series and geometric series. To start, we're going to look at this series. One, I wrote it down.
I'll write it down.
Wait, what's today's next?
Geometric power series as functions.
Geometric power series as functions. We're going to look at this series. 1 plus x squared plus x to the third, and it keeps going. When does it stop? Never. It goes on forever and ever and ever. It is an infinite series. Is it a power series?
Yes.
What is a power series? Coefficient times x to a power. Is this a coefficient times x to a power? Yeah, so it's a coefficient times x to a power. What's different is I have the same coefficient every time. What is that coefficient? 1. But it is a power series. It is a power series. It is also what type of series? It is geometric. Not all power series are geometric, but this one is a geometric series. Geometric series, there are two parameters that I look at. What are they for geometric series? A and R. What's A? A equals 1. It's your first term. And what do I multiply each time to get to my next term? What's R? And R equals x. So this is just a geometric series. A is 1. R is x. Do you like those little bars that I made? I made those. Thank you. So this is a geometric series. Do you also see that we could write this in sigma notation? We can think of it two ways. It's a coefficient. What's our coefficient always? 1 times x to a power. How would I write that variable expression? X to the n. I can also think about it geometrically, which we know that our general term for geometric, we start at 0, is a times r to the n. What's a? 1 times r, which is x. So this is the general form for that series. So this is the series that we're looking at. So geometric series, a equals 1 and r equals x. Your homework on Friday. How did you find interval of convergence? Ratio test, and that always works. We could perform ratio test on this, and figure out what the interval of convergence is, but we do not have to because it's a geometric series. On any other series, ratio test. This one is geometric, and we know something about convergence of geometric series. When do geometric series converge? When r, absolute value of r is less than 1. And what is r this time? X. So this is going to converge if the absolute value of x is less than 1, which we would write from -1 to 1. You could do that with ratio test and you get the same thing, but you do not have to because it's geometric. And the series converges to something that we know because it's geometric. What does it converge to? What do geometric series converge to? A over 1 minus r. And so in this specific case, what's A? 1. And what's r? X. So this series converges to 1 over 1 minus x. What that means, x is whatever we plug in. It's a function, so we can plug in values. Does that make sense? So if I plug in 0.5, the series is going to converge to 1 over 1 minus 0.5. If I plug in 0.7, this is going to converge to 1 over 1 minus 0.7. What's going to happen if I plug in 80? It's going to diverge, because that's not in my interval of convergence. What this means, and this is a huge deal, that this 1 plus x squared plus x to the third, what do we call these functions that are x to a power added up?
Polynomial.
Way to go, Zane. These are polynomials. So this polynomial looks like this function. What do we call this type of function? When it has a fraction. It's a rational. So do you see this is a rational function? And we're saying it looks like this polynomial. What this means is that the series and the function are almost equivalent for the x values in the interval of convergence. The series and the function are almost equivalent for the x values in the interval of convergence. It's a huge statement that I want to break down what that means. To do that, here, I'll give you a second. To do that, to like investigate this, I want to look at a PowerPoint that I did not make, so don't judge me. In blue, I have the rational function 1 over 1 minus x graphed. Do you see that that's a rational function? You see that asymptote? It looks like 1 over x. It's just been shifted. And my claim, because it's geometric, is that this function and this series are the exact same. They're equal. Which means if I plug in 0.5 here, I should get the same thing as if I plug in 0.5 to the series. What's hard is how many terms of this infinite series do I need to add up for it to be equal to this? Infinite. So it's never actually going to equal this. But the more terms that I go, the closer it gets. Does that make some sense? What if I only got 2 terms, 1 plus x? What kind of function is 1 plus x? It's linear. So I have my rational in blue, my linear in red. Do you see how the red function and the blue function match up a little bit? But not very well. So if I'm saying these things are equal, well, they're not really equal right now. How could I make them look more equal? More terms. I'm going to go out to my third partial sum, which is going to turn into 1 plus x squared. What should the red function look like now? It should look like a parabola. Do you see how that parabola hugs this function? It hugs right here, sort of between -1 and 1. It's hugging. How could I make it hug tighter? Yeah. Not the area, the actual y values. So you see how it's like on top of each other. If I do a cubic function, if I make a cubic polynomial, it hugs even tighter on the blue piece. I don't know if I have another one. No. So, but you see that if I added more terms, it would just hug that blue tighter. Is it ever going to hug every single part of that blue function? Where are the only x values it's going to hug? From -1 to 1. No matter how far I go, it's only going to match up between -1 and 1. Because that's where my series converges. Does that make sense? I could have a 100th degree polynomial. What's a 100th degree polynomial going to look like? Show me with your arms. It's going to look like this. There's going to be some stuff going on, but generally the end behavior is going to look like this. And it's going to hug that blue curve perfectly. Not perfectly. Really, 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 really well. And we can even see this if we plug it into our calculator. Someone give me a number between -1 and 1.
0.
That's boring.
0.5.
0.5. Okay. Let's do 0.3. Let's do something interesting. -0.3?
0.8.
Okay, I don't want any. Oh no, hold on. If I do 1 over 1 minus x, so that's the function 1 over 1 minus x. If I plug in 1 over 1 minus -0.3, I get 0.76923. That should be almost the same as if I plug into 1 plus x plus x squared plus x cubed. Do you see how that's my polynomial? This out 4 terms. That's at 0.763. If I add plus -0.3 to the 4th, it's going to get, if I put this plus negative 0.3 to the fourth, it's going to get even closer to.
You did plus negative 3.
It's because you can't square it. Yeah.
You can.
Why did they?
I don't know. Can we try again?
Yeah.
Don't watch this on YouTube. Don't like or subscribe.
Dislike and unsubscribe.
Negative 0.3 square. Oh wait, not square first. Plus negative 0.3 square plus. This is really hard to do. I feel like I'm on. So it should be really close to 0.769. I'm going to take that and add negative 0.3 to the fourth. Oh.
It's gonna get smaller right there.
Yes, it's alternating. Do you see that? So we're going to bounce around the value.
Oh.
Does that make sense?
Yeah.
Because it's alternating, because it's a negative. Ooh, that's really good that we tried this one.
You're welcome.
And so it's getting closer and closer to 0.769, but it's bouncing around it, because it's alternating. If I plugged in 0.3, would the series be alternating?
No.
No, so it would approximate 1 divided by 1 minus 0.3, 1 over 1 minus x, is that, and it will get closer and closer from below, because it's not going to be alternating. Here I'm adding and subtracting to get to that. Cool. That's really interesting. So what we're doing is we're approximating this rational function with this polynomial power series. Does that make some sense? I really hate these slides, but they have good information. You don't have to write it down. I hate what's happening. Okay, now that it's done. A function in a series behave almost the same on the interval of convergence of the series. Why do I say almost? Because it's an infinite series, so it can never actually equal what the function equals, but it's been behaved really, really close.
So why do they do that?
What?
Why do they do that?
Why do we approximate it with a series?
Why do they almost equal?
Because, like, why are they almost equal? Because the series a over 1, if our function looks like a over 1 minus r, that looks like 1 over 1 minus x. Does that make sense? So if our function looks like a over 1 minus r, then we can write it as a geometric series. Does that make some sense? If we can turn a rational function into a over 1 minus r, then we can write it either as a geometric series or as a regular function.
So because 1 over a minus r looks like 1 over
Exactly.
x, 1 minus x.
Because 1 over 1 minus x looks like what a geometric series converges to. Then we can write it as a series. Why we would want to do that, we will get to later. But it's just cool for right now. Today's just cool. We'll get into the applications of it later. Each partial sum is an approximation of your function. We can never actually get our function, but our partial sums approximate it. And I'll wait. The more terms that are included in the partial sum, the better the approximation. So we are going to look at another, actually, no. First, what you're going to do is memorize this. This infinite series, 1 plus x squared plus x cubed, all the way to x sub n, which is the series from 0 to infinity of x to the n, it equals 1 over 1 minus x. That function and that series look exactly the same, only between -1 and 1. And they do actually equal each other, but only if you get to infinity, which you can't do. You have a pop quiz.
Pop.
Probably on Monday. That asks you, take this function, write the series for it. Because it's not on the internet. No one knows about it, except if you come to class. It is not on our outline, but I'm pretty sure you have a pop quiz on Monday. Actually, yes, the internet does. You have a pop quiz on Monday. I'll tell you about it like 7 more times before you have it.
Isn't that the pop quiz that you told us?
Oh, yeah.
This is the pop
That
quiz.
you tell us.
Yes, I'm telling you now that you have a pop quiz. And one of the questions on it will be, I give you 1 over 1 minus x, and I'm like, what's the power series? And you say, the sum from 0 to infinity of x to the n. It's a really, really easy quiz. There are 3 more questions. All of them are, what's the power series for this function? Everyone gets 100 on this quiz, unless you decide you don't want 100. Okay, so let's try another one. Oh, we don't have time. We're going to go to lunch, and then we're going to try this. Hi, James. Bye, Nishani, if you watch this, and bye, everyone else. Hi, Lewis. We miss you. You should watch this, and we hope that you're well. So we're going to start with this example, expressing the function f of x equals 1 over 1 plus x squared as a power series, and finding the interval of convergence. Is that funny, Lauren?
No. Sorry.
So what makes us think maybe we could write this function as a geometric power series?
1 over a over 1 minus r.
Because you see that the function sort of looks like a over 1 minus r. That's what makes you think maybe we could write this as a power series. That's a really, really good question that Catherine asked. So what we want to do first, because this sort of looks like a over 1 minus r, it is the root of arcane. That's true. We are going to do something sort of with that tomorrow. We're going to get back to derivatives and integrals tomorrow. It's been a while.
That's not.
So our first step is we look at that function. We think, ooh, that sort of looks like a over 1 minus r. Well, let's actually rewrite f of x as a over 1 minus r.
Later I'll try to lunch. James Snapchatted me and said, what's a power series?
So we're going to rewrite the function as a over 1 minus
So I
r.
think he's
The function we have it right now as 1 over 1 plus x squared. Is it a over 1 minus r right now? Is it close? What's the only thing we're missing? The minus. We have an a, we have an r, but it's not minus. So we just have to write this as 1 over 1 minus negative x squared. Perfect. That's our first step. Is we want to write it as a over 1 minus r.
So you're
Yeah, so what's your a?
1.
1. And what's your r? Good job. Negative x squared. So now we have our a and our r. Once we do that, our second step is going to be to replace a and r in the general geometric power series. What is our general geometric power series? What does it look like? Our general geometric series. Perfect. A times r to the n. That's what a geometric series looks like. And what is our a?
1.
1. So I'm not going to write it. What's our r?
Negative x.
Good. Negative x squared. Then. So good. That's how we write it as a series. Generally, I like to separate my coefficient and my variable expression. Power series, I really like to see what's my coefficient, what's my variable expression.
Negative x.
So what can I pull out that's not really, that's attached to the x, but not part of it?
Negative 1
Negative 1
to the
to the n. Good.
Oh.
And how can I write my variable expression?
x to the 2n.
X to the 2n. That's how I prefer to write it. It's not like right or wrong, but I like to separate my coefficient and my variable expression. I also, once I get to this point, like to plug in a few terms and just write out the first few terms of this power series, which makes what type of function?
No.
A polynomial. So it should make some polynomial. I don't like to write out the first two terms to sort of see this polynomial that's being made. If I plug in 0, I get 1. Why is it really good that when I plugged in 0, I got 1? Because that's what A is. So this is a good way to check that you did it correctly. If I plug in 1, I get negative x squared. Is that what I should have gotten based on my R? Yeah, I took 1 multiplied by negative x squared.
Oh.
Do you see that?
Yeah.
Let's plug in 2. So let's not use the A and the R. Let's use our series and make sure it gives us what the A and the R told us to get.
1.
So plug in 2, and I get negative 1 squared, which is positive 1, plus x to the 4th. Is that what I should have gotten with the R that I have?
Yes.
My next term would be negative x to the 6th,
And so on.
and so on. So I can see that I do have the correct A and R. This is my power series representation. This is the way that I really like to see it written. Does that series look like this function always?
No.
No. There's only when that series converges. So we need to find the interval of convergence. Generally, how do you find interval of convergence? Ratio test. And you could ratio test this, but we don't have to because it's geometric. So because it's geometric, we know this is a geometric series with A equal 1 and R equals negative x squared. We know it's geometric, which just means that the absolute value of our R has to be strictly less than 1. That's what a geometric series tells us. So this is how we can figure out it's going to converge when that's true. And then we just have to solve that inequality for x. What should we do first? Yeah, so the absolute value.
Negative 1.
I am going to put it between negative 1 and 1. I'm also just going to go ahead and drop that negative because it's positive. So that's what I'm going to do first, and then I'm going to put
No.
x squared between this negative 1 and 1. And this is actually sort of hard, because what do I usually do to get x by itself?
Square.
Square root. And what's a
Root it.
huge red flag?
I.
Yeah, it's imaginary, which we don't have to deal with in this calculus class.
Immediately red flag.
Immediately, there's a red flag. I'm going to draw it. This is for James. What? You think it should be the other way? Why? The flag's blowing the wind.
Yeah, but she's going to the right.
I was thinking of the flag that's like.
Oh, like a rectangular flag?
Yeah.
I don't know. Yeah, I don't know why.
What's a blue star? You gotta make like.
It's not an American flag.
Make sure.
Okay, so this is weird because we can't square root a negative. So really, x squared has to be between 0 and 1. Do you see that? But then, for x squared to be between 0 and 1, what does x need to be between? Or negative 1 and 0. Do you remember when we did that on Jeopardy?
Yeah.
So really, for x squared to be less than 1, you can have negative values for x. So when you're solving that inequality, x has to be between negative 1 and 1, but realize that you're not taking the square root of negative 1. You're saying for x squared to be less than 1, x can be between negative 1 and 1. And that's just thinking, like, theoretically about it. You could do a sign line, put x squared between 0 and 1, like do a sign line and figure out when that's true, but I don't want to. I can just see this between negative 1 and 1.
Alright.
Does that make sense? You can look at it and be like square root of negative, but that's not what you're doing. So we found the interval of convergence where this series looks like that. If you graph them on top of each other, they would lie perfectly on top of each other between negative 1 and 1, as long as your polynomial was what degree? Squared isn't going to fit it perfectly. Cubic's not infinite, so it's got to be an infinite degree polynomial. But if we did 100th degree, it would be pretty much perfect. Like Phil. Phil's pretty much perfect. Not completely perfect,
Yeah.
but pretty much. Feel okay with that? Feel okay with that?
Yeah.
Okay. Let's do another one.
Example.
We're going to express the function 1 over 2 plus x as a power series and find the interval of convergence. What makes us think we might be able to write this as a power series?
Geometric.
It looks like what? A over 1 minus r. If I tried to tell you to write sine x as a power series, you'd be like, that does not look like A over 1 minus r. I can't do that. But I'm not asking you. I'm asking you to take rational functions, write them as power series.
It looks like it, but you can actually do it.
Can you give me an example?
No.
Okay.
I was asking if you could.
I can't think of a rational function with a binomial on the bottom and a constant on the top that you couldn't do it with.
Does it have to be 1 over 1 minus x? So we're gonna have to
It has to look like A over 1 minus r. We are going to have to get rid of the 2. It has to look like A over 1 minus r. A and r can do whatever they want, but that 1 has to be there. So yeah, that's our first step, is that we need to write our function 1 over 2 plus x as A over 1 minus r. So the only thing that has to be there is a 1 and a minus. So let's get rid of the 2. How do we get rid of the 2?
Subtract. Just kidding.
What can we do to both the top and the bottom?
Times 1/2.
Times by 1/2 the top and the bottom, which is really just multiplying by 1, right? So I'm going to multiply the top by 1/2. What do I get? 1/2. And multiply the bottom by 1/2. What does the 2 become?
1.
Plus 1/2 x, or x over 2. So now I have A over 1 plus r.
And your A is 1/2.
But I'm not done, because what do I not have?
Negative. No,
Minus. So I'm just going to do minus negative. Good. So now it's A over 1 minus r. My A is 1/2, and my r is negative x over 2.
How do you know that A is
Then I take my A and my R and I put it in the general form of a power series, a geometric power series, which is A times R to the n. What's A?
1/2.
What's R?
X over 2.
Then. And so I'm done with the hard part. Now I just sort of want to simplify that and separate my coefficient from my variable expression, just because I like it. So the 1/2 can just stay. What happens to the negative x to the n? How can I split that up?
Negative 1 is
n over 4.
Negative 1 to the n x to the n. So I can split up negative x to the n over 2 to the n. So I just raise every factor in there to the n power. And then I want to make it look better. The top looks good, negative 1 to the n, x to the n. Be careful if you're being taped for this, so don't say something dumb. How can I simplify 2 times 2 to the n? I said that with love in my heart. Don't say something dumb.
2 to the n.
Exponent rules. Exponent rules. Same base, multiply. What do you do with their exponents? Add.
So it'd be 4 to the n plus 1.
2 to the n plus 1. Good. If you had 7 2's here, multiply by 2 again, now you have 8. There's always one more because you have an extra 2 in there. Does that make sense?
I see.
Same base, add your exponents. So that's a really nice power series representation of this function. I'm going to write out the first 4 terms using my series just to be sure it looks like what I want it to look like. I plug in 0, I get 1, 1 on top, and then 2 on the bottom.
1/2.
Is that good?
Yeah.
Yeah, that's what I wanted. Then I'm going to plug in 1, and it's going to be negative x over 2 squared, which is 4. Did I multiply by negative x over 2?
Yes.
Great. Let's try 2 more. Plug in 2, I get positive x squared over 2 to the 3rd. I multiply by negative x over 2 again, that's good. And then I plug in 3 and I get negative x to the third over 2 to the 4. So it does look like what I wanted it to look like. So the cool thing is that this series looks like that function. Everywhere?
No.
No, it's only going to converge. I could ratio test, but I don't have to because it's geometrics. I can just take my r, which is negative x over 2, and make the absolute value of r less than 1. Which means that x over 2 is going to be between negative 1 and 1. And x is going to be between negative 2. Oh no, I hate messing up on videos. Because I have animations for these. You want to see them?
Sure.
You want to see them?
Yeah. Yes.
Yes, everyone's so excited. Calm down. So the first example that we did, 1 over 1 plus x squared. Look back at the first example. Is this what we got? If we do the second partial sum, that means we're graphing parabola. Do you see how it hugs the blue function between negative 1 and 1? We can make it better by doing a 4th degree. And now it's a upwards facing 4th degree. Or a downwards facing 6th degree. And it's just going to hug it more and more tightly the more terms that you go. But only between negative 1 and 1. The one we just did, I don't have an animation. But that's a 3rd degree, so it's a cubic function. And you can see how the cubic function hugs that rational function between negative 2 and 2. It doesn't really hug that well right here, right? Do you see that? There's a pretty big gap. What could make it hug better? More terms. The more terms, the more it's going to hug. Cool. Let's do one more together, and then I'll have you try one. That feels like that feels to me like a really good use of your time, Phil.
When did you do that?
Today or?
Yeah, I got it today too. Not in this class, but
Why?
You got it today and
You got
yesterday.
it.
In case it changed.
yeah.
Okay, so x over 1 plus 2x as a power series and finding the interval of convergence. What makes us think we can write this as a power series? Looks like a over 1 minus r, sort of. It's a monomial over a binomial, which are all types of polynomials, which we all know.
So, like, what are we supposed to trying to find them?
We're trying to find a series and we need this to be a over 1 minus r. Do we have a 1?
Yeah.
But we don't have a minus, so we'll have to make it. What's a? And what's r? Negative. Then we want to write this as our general geometric series, which is a times r to the n, which is fine. It just doesn't look that good. So I want to separate my coefficient and my variable expression. So that x I'm just going to leave for now and do negative 2 to the n times x to the n. How can I make that look even better?
Add the x's.
Add the x's. So I have 1x here and n x's here. So how many do I have? X to the n plus 1. So my coefficient is negative 2 to the n, and my variable expression is x to the n plus 1. And let's write out a few terms and make sure. So I don't really look at my a and my r. I just want to look at my series. This is a little, oh no, this one's not that weird. Plug in 0, you get x. Is that good?
Yes.
Yes, because that's what I expected a to be. Plug in 1, I get negative 2x squared. Did I multiply by negative 2x? Plug in 2, I get 4 x to the third, so I multiply by negative 2x again. So I found a series representation for this function, but it's only gonna hug that curve when the absolute value of r is less than 1, which means 2x has to be between 1 and negative 1, which means x has to be between negative 1 and 1/2. So it doesn't have a very big interval of convergence.
So we don't endpoints.
No, that's a really, I meant to talk about that before.
Oh, yeah.
Why are we not taking endpoints even though we have an interval?
Because this is different.
No, the one.
Because we know that 1 diverges for geometric. Ratio test, when it equals 1, it's inconclusive. But geometric series, it has to be strictly less than, equal to 1 for R diverges.
Okay.
Does that make sense? If you're ratio testing, you better check your endpoints. But if you're using the geometric series test, you don't have to check your endpoints. What? It's always parentheses. Always parentheses. Why are you smiling? Are you having fun?
Yes.
Me too. I really like this. Next one. Oh no, I'm not. I'm done. You try. James and Lewis and Nishani, you should pause the video now and unpause when you're done trying. Did everyone get a equals 2 and r equals x over 2?
Yeah.
That's easy, yes. You just divide by 2 to get the a over 1 minus r. Then we are going to write it as a times r to the n, and then we want to make it look pretty. So we're going to leave the 2 for now, times x to the n over 2 to the n. Everyone good with that?
Yeah.
Then we have the same base. 2 is the base on 2 of the pieces. Does that make sense? So we want to simplify that. I want to, because I think it'll look prettier. If we have 2x to the n over 2 to the n, how many 2's do we have on top? 1. How many do we have on the bottom? N. So we're definitely going to have leftover 2's in the bottom. Does that make sense?
Wait, why?
Because there are way more 2's on the bottom than on the top. So if I had 2 over 2 to the 5th,
Oh.
what would that simplify to? Perfect. 1 over 2 to the 4th. If you have 5 2's on the bottom,
Oh,
one of them cancels.
Let's do the ends for the x, not the. Wait, it's 2 times x to the n?
Yes.
Okay.
So I know I'm not going to have any 2's left on top. The x to the n is going to be up by itself. How many am I going to have on the bottom? N minus 1. 2 to the n minus 1. Because one of them is going to cancel out on top. I'm going to have 1 left on the bottom.
I have to do that.
Yeah.
So I got the same. I got the right.
Right, so like this is okay. It's just not as pretty as it could look. And I do, if you have the same base, I want you to go ahead and simplify that. So this is the series that I really like. But it's actually sort of weird to plug into though. If I plug in 0, what do I get on top? 1. And what do I get on the bottom?
2 to the negative 1.
2 to the negative 1. So what is that?
2.
Just a 2 on top, which is my first term. Does that make sense? 1 divided by 2 to the negative 1 is just 2. Then I plug in 1 and it gets easier. X over 2 to the 0, so it's just x. Did I multiply by x over 2?
Yeah.
Yeah. And then I plug in 2 and I get x squared over 2, so I multiply by x over 2 again. This is going to, so this series looks like 4 over 2 minus x, but it's only going to look like that when the absolute value of r is less than 1, which means that x is going to be between. Mhm.
I was kind of confused getting it to look pretty. So what I did was I found the terms and then I did
Okay, you can do it that way.
okay.
I wouldn't count on that all the time, but if you get really stuck, sure, that's like a good way to do it. Because you know what the terms look like if you have a and multiply by x over 2 each time. Last 2 things. These are super fast. We want to write these power series as functions. So the first one we're going to look at is the series 2x all to the n and the series 3x to the n. So my claim is that these power series we can actually write as functions in f of x equals form. What makes me think that? Because it looks like AR to the n. Does that make sense? If my function looks like a over 1 minus r, I can write it as a series. If my series looks like AR to the n, I can write it as a function. So this is pretty easy. All I have to do is figure out, well, what's a and what's r. So this should look like a over 1 minus r. That's what that looks like. And you're done. Except I want to know, when does it look like that? That's only going to be true when r is less than 1. So when x is between -1/2. Does that make sense?
Yeah.
Does B look like the series A r to the n? Kind of. We have to do a little bit of work to really make it A r to the n. Do we have an A? Yeah, we have something that's not raised to the n, it's by itself. So 3 is our A. But what's being raised to the n? X squared. So now it's AR to the n. A equals 3. R equals x squared. And so my function is a over 1 minus r. But that's only going to be true when r is less than 1, which we said before. When is x squared between -1 and 1?
-1 to 0.
-1 to 0 and 0 to 1. So it's also x. So we can go backwards. Any questions? Any words for our absent friends?
Get better.
Feel better. Cool. You should look at your homework online. Bye.